Today we will continue with potential energy and energy conservation. We will see different types of potential energies, gravitational potential energy, elastic potential energy, and the relation between these two potential energies, and also the relation between potential energy and kinetic energy. We will discuss all these things. We will learn how to use gravitational potential energy in problems that involve vertical motion. And we will also learn how to use elastic potential energy in problems that involve a moving body attached to a stretched or compressed spring. So we will do many examples with springs. And during the next lecture on Thursday, we will discuss the difference between conservative and non-conservative forces. And finally, we will finish this chapter with the energy diagrams to understand how an object moves under the influence of a conservative force. So let me start with this example. Here you see a sandhill crane, in Turkish Kanada turnası. This sandhill crane glides into a landing. It descends along a straight line path at a constant speed. During the glide, what happens to the mechanical energy, the sum of kinetic energy and gravitational potential energy? So during this lecture, we will learn how to answer this question, okay? What happens to the mechanical energy? Mechanical energy is the sum of kinetic energy and gravitational potential energy. We will learn today. And we will see that we can think of energy as being stored and transformed from one form to another. So we will see all these things within this part of my lecture. Let me start with the gravitational potential energy. Here we have a ball, let's say particle. When a particle is in the gravitational field of the Earth, there's a gravitational potential energy associated with the particle. And this gravitational potential energy is given with this expression, U gravitational. And here we have mg. M is the mass of the particle, and y is the vertical coordinate of particle. So you can consider that the distance between this particle and ground, okay, something like this. So here, what happens when the basketball stays at this position? It has certain gravitational potential energy, and when it descends, gravitational potential energy is converted to kinetic energy and its speed increases. So we will learn the details of this gravitational potential energy in this part. So now let's try to find the work done by the weight when the body moves downward from a height y1. So let's consider that here we have a box with mass m, okay, and the distance or the height of this box from the ground is given with y1 here, okay. And then it goes down, okay, because there is a weight acting on this box. And there can be another forces acting on this box, for example, air friction, okay. But now I would like to calculate the work done by the gravity, okay, the work done by the weight. So what about the displacement? This was the initial position of the box here with the height of y1, and this is the second position of the box, which is given with y2, and this is the displacement vector with the blue color here I show, okay? Then what about the work done by the gravitational force? Force times displacement, and force is given with W, m times g, and displacement is given with y1 minus y2. Okay, this is the displacement here. And if you open this weight with mg, and here we have mg y1 minus mg y2. So what do you see here? Here we have two terms. This mg y1 is equal to the gravitational potential energy when the position is y1 here, and this mg y2 is equal to the gravitational potential energy when the position is y2 or position 2, let's say. Okay, so what do you see here? We have u gravitational 1 minus u gravitational 2. If you take this minus to the outside of the bracket, let's say, and here within the bracket we can have u gravitational 2 minus u gravitational 1. You see, these two terms are equal to each other. So what we have here, u2 minus u1, what is this? This is delta u gravitational. Okay, so the work done by the gravity, the work done by the weight is equal to the change in the gravitational potential energy, but with negative sign. Okay, so don't forget this one. The work done by the gravity, by the weight, is equal to the change of the negative sign of gravitational potential energy. So we can write it like this. Any question here? Okay, then let me discuss the two conditions. Here in this condition, as we have discussed here, we have box, and this has certain height which is given with y1, and this box is moving downward. Okay, then there are forces acting on this box, and I am dealing with the work done by the gravity, work done by the weight. Okay, so displacement here with the blue color is downward, and y here, what is the y? This is the height of the box. Y decreases. Okay, so weight does positive work because the direction of the force of weight and the direction of the displacement are same. Okay, so then the work done by the weight is a positive work. And what about the gravitational potential energy? Look at this equation here, which we have obtained. The work done by the gravitational force on a particle is positive, and the change in the gravitational potential energy of the particle is negative, because if it is negative, you multiply with negative sign here, then the result will be positive. Okay, so if this is positive, this delta U is negative. Don't forget. You can also understand this one. What happens at the beginning here when the position is, the height is y1, have potential energy which is given. Let me write here. Here we have potential energy gravitational 1, which is equal to mg y1. Here the potential energy U gravitational 2, which is equal to mg y2. So since y1 is bigger than y2, then the first gravitational potential energy is bigger than the second case. Okay, so what do you see here? What about delta U gravitational? Delta U gravitational is U2 minus U1. Okay, so since this one, the first gravitational potential energy is bigger than the second case, then this will have a negative sign. This will be negative, okay? So then the delta U, the change in the gravitational potential energy is negative. What is the meaning of negative? Gravitational potential energy decreases, okay? This is the meaning of the negative number for the change in the gravitational potential energy. So now let me discuss the second condition when the body moves up, okay? Second condition. Here we have a box, and this is the initial condition of the box. This is the height of the box, which is given with y1, and we apply F other, and we are moving this box from this condition to this condition, okay, this position. So now we have y2. This is the height of the second position for the box. What about the displacement? We move the box from this position to this position. So then we have displacement like this. And what about the weight? Weight is in this direction, opposite direction. So if you would like to write the work done by the gravity, it will be negative because this is the direction of the weight and this is the direction of the displacement with the blue color. Displacement is in upward, but the weight is downward. Then the work done by the weight is negative, okay? Weight does negative work here. And what about the gravitational potential energy? If you write this expression, work done by the gravitational force is equal to the delta U gravitational. So if this is negative, then this must be positive. So then this result will be negative, okay? This is the sign of the gravitational potential energy and the change in the gravitational potential energy. Do you have any question here? So now let me give you another caution from the book. To what body does gravitational potential energy belong? So here we have written the gravitational potential energy like this. G, Y, let's say, okay, height of the box or height of the object. So does this gravitational potential energy belong to this box? No, you cannot say like this because what do you see here? Within the gravitational potential energy, we have mass of the object, but in addition to that, we have G here, okay? We have G, so G is the property of the Earth and mass is the property of the object. So you cannot say that this gravitational potential energy belongs to this box. So this is explained here. So the gravitational potential energy is shared property of the body and the Earth. Okay, so this is important. So now let me continue with the conservation of mechanical energy. So here you see a mechanical energy. What is the meaning of mechanical energy? Mechanical energy means that we are talking about kinetic energy, which we have learned during the last lecture, plus potential energy. Okay, so this is called as mechanical energy and shown by E. Okay, so now we will discuss the conservation of mechanical energy. So let's consider that we have a body and there is only force acting on this body, which is the weight of this body, and F other, let's say friction forces or air friction, fluid resistance, all other forces are zero, okay? There is no force acting on the body than the weight of its body. Then let's consider that, let me choose the pointer. This body is falling freely with no air resistance and can be moving either up or down. Let its speed at point y is v1 and its speed at y2 be v2. Okay, then let's apply work energy theorem. So during the last lecture we have learned work energy theorem. The total work done on the body equals the change in the body's kinetic energy. This is the change in the kinetic energy. This is the final kinetic energy minus initial kinetic energy. We have learned this one during the last lecture. This is the work energy theorem and valid for all cases. Don't forget this one. The total work done on the body is equal to the change in the kinetic energy of the body. So now, if gravity is the only force that acts on this body, this was the initial condition, so then what about total work done on the body? The total work is given with the gravitational work, and the gravitational work is given with minus delta U gravitational, which we have learned here, okay? The gravitational work on a particle is given with minus delta U gravitational. The total work done on this particle is given with delta K, and we consider that the total work done on the particle is only given with the gravitational work if you consider other forces are zero, okay? And then this is equal to minus delta U gravitational. And we know that it can be written like this, U gravitational 1 minus U gravitational 2. So here we have V total. Look at this one. And here we have another V total. So they are equal to each other. So then I can write this expression. Delta K is equal to minus delta U gravitational. You see? Here I have a delta K, and this delta K is equal to minus delta U gravitational. So then I have this expression. So what is the delta K? Delta K is K2 minus K1. And what is minus delta U gravitational, which is given with U gravitational 1 minus U gravitational 2. So if you take this K1 to the right side, and if you take this U2 to the left side, finally you can get this type of expression. Look at the equation 7.4, this one. K1, initial kinetic energy of the particle, plus U gravitational 1, initial gravitational potential energy of the particle, equal to K2, final kinetic energy of the particle, plus final gravitational potential energy of the particle. So what we see here, on the left side, we have K times U, kinetic energy plus potential energy, and this is the mechanical energy. So this is the initial mechanical energy of the particle, K1 plus U1, let's say, okay? So if there is no other forces acting on this object, or if only the gravitational force does work, then this initial mechanical energy is conserved, and this K2 plus U2 is equal to this one. Okay, I can also write this one. Let me choose the pen here. So what is this? This is the initial mechanical energy of the particle and this is the final mechanical energy of the particle or object, okay? Then E1 initial mechanical energy is equal to the final mechanical energy if only the gravitational force does work, okay? Then the mechanical energy is conserved. Okay, so here let me give you some more information about the conservation of mechanical energy. The total mechanical energy of a system is the sum of its kinetic energy and potential energy, as we have discussed. A quantity that always has the same value is called a conserved quantity. When only the force of gravity does work on a system, the total mechanical energy of that system is conserved. Then we can write this conservation of mechanical energy for this condition. And you already know from the last lecture that the initial kinetic energy can be written with 1/2 mv1 square, and the final kinetic energy also can be written with this form, 1/2 mv2 square, and the gravitational potential energy for the first case can be written with mgy1, and the final gravitational potential energy can be written with mgy2. This is the conservation of mechanical energy if only the gravitational force does work on an object. Now let me give you a few examples. Any question? So here there is the athlete, let's say, okay, and then he jumps. So just after he jumps, he has certain kinetic energy, okay? So he produced this kinetic energy with his muscles, okay? At the beginning here, look at this initial condition. Let's say this condition is 0 origin, and it has no gravitational potential energy. And let's consider that it is at rest, it has no kinetic energy, okay? But by using his muscles, he jumps, and now he has some certain kinetic energy. And since he jumped, he also has gravitational potential energy because he has certain height from the ground, okay? So what happens during this type of trajectory of this athlete? So when he is moving up, what happens? The kinetic energy will decrease, right? And gravitational potential energy increases. So at the maximum height, he will reach the maximum gravitational potential energy, but at the maximum height, its kinetic energy will be 0. Let me write here. Let's consider that here at this maximum height, his velocity is 0, momentarily at rest. For this reason, his kinetic energy is 0 since the velocity is 0 momentarily. And then at this condition, gravitational potential energy is maximum, okay? Because he reaches to his maximum height. So what happens during this type of movement? When he is moving down, kinetic energy increases and gravitational potential energy decreases, okay? So after he jumped, let's consider this condition, this part. So here, the total mechanical energy is equal to the total mechanical energy here, and total mechanical energy here, and total mechanical energy here. So during this type of movement, at every point, the total mechanical energy, kinetic energy plus gravitational potential energy, is always same, okay? But at the beginning, before he jumps here, the total mechanical energy is 0. Also here, when he stops, let's consider this is the origin and U gravitational is 0. And since he stopped, kinetic energy is also 0. So total mechanical energy is 0. So we have the same condition here. Kinetic energy is 0 and gravitational potential energy is 0 before he jumps. Any question here? Is it clear for you? Okay, another example. This is bioapplication, converting gravitational potential energy to kinetic energy. This is a kingfisher, in Turkish yalı çapkını veyahut da balıkçıl diye biliniyor. When a kingfisher spots a tasty fish, the bird dives from its perch with its wings tucked in to minimize air resistance. So what do you see? Look at the shape of the kingfisher here. Look at the shape of the bird. So it tucks its wings into a minimum volume, okay? So then the shape, the volume of the bird decreases. Remember the air resistance. The friction force due to the air resistance is given with the shape of the object and also velocity of the object. So if you decrease the volume of the object, okay, if you change the shape of the object, then you can decrease the fluid resistance, you can decrease the air resistance. So the bird is doing this, minimizing air resistance. Effectively, the only force acting on the diving kingfisher is the force of gravity, so mechanical energy is conserved. So since only force of gravity acting on this bird, mechanical energy is conserved. What was the mechanical energy? Mechanical energy is kinetic energy plus gravitational potential energy. The gravitational potential energy lost as the kingfisher descends is converted into the bird's kinetic energy. So let's consider that at the beginning, this bird is staying here. Let me draw. Let's consider this is the initial position of the bird, let's say y1, and kinetic energy here is 0 because it is at rest. And what about the gravitational potential energy? Gravitational potential energy here is maximum. And here there is a fish, okay? And let's consider that this is the surface of the water. And here y2 is 0, you can take. And then your gravitational 2 is 0. What about the kinetic energy? Kinetic energy is maximum, okay? Because the initial gravitational potential energy here is converted to the kinetic energy. So final gravitational potential energy is 0, initial kinetic energy is 0, and at the beginning the bird had gravitational potential energy, and this energy is converted to the kinetic energy in the second condition. So the gravitational potential energy lost as the kingfisher descends is converted into the bird's kinetic energy. Since the total mechanical energy is conserved, this is the total mechanical energy for the first condition of the bird, and this is the total mechanical energy for the final position of the kingfisher. Any question here? What about the choosing of origin? For example, here I have chosen that this is origin, and here the height is 0, okay? For the vertical axis, I have chosen that this is the origin. You can also choose that this is the origin. It depends on you, and the result will not change, okay? So choose 0 height to be wherever you like. when working with gravitational potential energy, we may choose any height to be y is equal to 0. This is the caution from the book and very helpful information when you are dealing with the gravitational potential energy related questions. So now let me show you the first example from the book of this chapter, height of a baseball from energy conservation. You throw a 0.145 kilogram baseball straight up, giving it an initial velocity of magnitude 20 meters per second. Initial velocity is given and mass is given. Find how high it goes, ignoring air resistance. So maximum height is asked. So here we have the drawing of the baseball. Here, this is your hand, and you apply a certain force on this baseball, and then at the beginning, this baseball gains this velocity, initial velocity, and it has certain mass. And after the ball leaves your hand, the only force acting on it is gravity. So the ball is moving in this direction, and when it reaches to its maximum height, the velocity is 0. Kinetic energy in that condition is also 0, but the gravitational potential energy at the second condition is maximum, okay? If you choose this position, initial position is y1 is 0, then here the gravitational potential energy will be 0. Now, on the right side, we have some colored bars. Look at them carefully. Here, for the first case, you see this bar with yellow color, let's say. Here we have E, total mechanical energy, and the total mechanical energy is completely given with the kinetic energy at the beginning, because this baseball has certain kinetic energy at the beginning, which is given with K1. And what about the gravitational potential energy? At the beginning, this baseball has 0 gravitational potential energy because it is staying at the origin, okay? So the total mechanical energy, E, is only given with kinetic energy for the first condition. This is 0. And when you throw the ball and it reaches to its maximum height, then here kinetic energy is 0 because velocity is 0. Then look at this one. Kinetic energy here in the second condition is 0. And gravitational potential energy is maximum, and the total mechanical energy is only given with gravitational potential energy. U2 maximum, okay, and this kinetic energy is 0 now in that condition. So what was the question? What is the maximum height? So it is very easy. Since there is only gravitational work on this baseball, okay, then total mechanical energy is conserved. So I can write this expression, E1 is equal to E2. So what we have E1, in E1 we have K1, this is 0, gravitational potential energy for the first case is 0, so E1 is only given with K1, and in the second case, E2 is only given with the gravitational potential energy. Then they are equal to each other since the total mechanical energy is conserved. Then write the initial kinetic energy here, 1/2 mv1 square, and it is equal to the gravitational potential energy at the maximum height mgy2. Then if you take from this expression y2, you can find 20.4 meter. Any question here? Okay, up to this point, we have considered that only gravitational force does a work on the object. So what happens if other forces also do a work on the object? So what will happen? So here, let's consider that on the right side again, we have a box. This is the initial condition of the box, which is given with y1. And this is the second position of the box, y2. Okay, what do you see here? There is a weight acting on this box downward, okay, which is given with mg. And there may be another forces, F other, okay? There may be here tension force or air friction, okay? Let's consider there is also other forces acting on this box. And let's consider that these other forces do work on this box. So then what happens? So the total work done on this box, V total, W total, is given with gravitational work. This is the gravitational work due to the gravitational force times displacement plus V other. So now you must be very careful. If you are dealing with the forces other than gravity do work, what about the sign of the works here? So since the box is moving down, this is the direction of the displacement. Blue color here shows the displacement vector, okay? So this is downward direction. And what about the direction of the weight? It is also downward. So since they are in the same direction, then the gravitational work is positive. But what about the V other here? F other is upward direction and displacement downward, then V other will be negative. V other will be negative, okay? You must be very careful when you are dealing with V total in mechanical energy calculations, okay? So now from the work energy theorem, we know that W total is equal to the delta K. Total work done on the object is equal to delta K. So now let's go back here. The total work is given with W gravitational and the work done by other forces. And it is equal to delta K. Let me write it here. W total work done on the box or particle is given with delta K. And here we have gravitational work plus other work. Okay, so what was delta K? Delta K is written with K2 minus K1. Then I can write this expression. W other plus W gravitational is equal to change in the kinetic energy. So I write this expression by using work energy theorem. So what about here gravitational work? Gravitational work is written with this expression. Gravitational minus delta U gravitational, and it is written with U gravitational 1 minus U gravitational 2. Then put this one into this equation. And then finally we have this expression. What do you see here? Other work done on the box with other forces plus gravitational potential energy for the first position minus gravitational potential energy for the second position, and all these things are equal to the change in the kinetic energy of the box. Okay, so what we have here we have U gravitational 2, take this one to the right side, and here we have kinetic energy 1, take this one to the left side, so then you can get this expression. Initial kinetic energy plus initial potential energy, gravitational potential energy, plus V other is equal to final kinetic energy plus final gravitational potential energy. So what about the sign of work other? The sign of the work other can be positive. The sign of the work other can be negative, like here. And the work other can be also 0, okay? There are 3 conditions for this other work. It can be positive, it can be negative, or it can be 0. And you must be very careful when you are dealing with V other in calculations. So in the second midterm exam, probably you will have such question, okay? And you must be very careful with the sign of the V other and how to determine the sign of the V other. So we know that work is force times displacement cosine phi, right? So you must be very careful with the direction of the force and the direction of the displacement and the angle in between. Here we have F other, for example, and direction is upward and displacement is downward. The angle is 180 degrees, then this will be negative. Okay? You must be very careful. So if you open this kinetic energy here, this is the initial kinetic energy, which is given with 1/2 mv1 square. This is the initial gravitational potential energy, mgy1. And here we have V other. And here we have final kinetic energy. Here we have final gravitational potential energy. Any question? The work done by all forces other than the gravitational force equals the change in the total mechanical energy. So look at this one. It is very important information. Look at this one. What is this? This is initial mechanical energy, right? What is this? Final mechanical energy. And here we have V other. If the sign of the V other is negative, then final mechanical energy will be decreased. If the sign of the other work is positive, then final mechanical energy will be increased. If the other work is 0, then initial mechanical energy will be equal to final mechanical energy. Okay, so here we have example for the forces other than gravity to work. Here you see a guy, parachutist, let's say, okay? So what about the forces acting on this guy? Weight downward, okay? And displacement downward. And there is F other here, which is the air resistance. It is upward, okay? So what about the work done by the gravity? Weight is downward, displacement is downward, then the work done by the gravity is positive. What about the work done by the other force, air resistance? It is negative because the direction of the F other and the direction of the displacement are opposite to each other. So then we have negative V other here. So the final mechanical energy of this guy must decrease. Okay, so then his speed remains constant. because K is constant. Normally, if there is no air resistance, let's consider this condition. Parachute doesn't open, and then ignore the air resistance, and this guy goes down, okay? So only weight acting on this guy, if you ignore air resistance in this case, okay, or very small compared to this first condition on the left side. So only weight acting on this guy here. Then what about the conservation of mechanical energy? Kinetic energy 1 plus potential energy 1 is equal to kinetic energy 2 plus potential energy 2. Okay, so let's consider that it is started from the rest and K1 is 0. Okay, and this is the initial gravitational potential energy mgy1. Okay, and let's consider that this is the ground and it goes the ground. So final gravitational potential energy here when the y2 is 0 is 0. And what about the final kinetic energy? So final kinetic energy will be equal to the initial gravitational potential energy. Okay, so the velocity, final velocity will be huge compared to final velocity here. Now let's try to calculate the final velocity on the first condition if we have F other. So this is the K1 and U1 plus V other due to F other is equal to K2 plus U2. So what about the sign of the V other? It is negative. Okay, because F other and S are opposite to each other. So then this final mechanical energy will be lower than the initial mechanical energy. Why? Because some part of the initial mechanical energy is lost due to the V other. Okay, then what about the final velocity? This final velocity will be lower than the final velocity in this case. Any question here? Okay, let me continue with example 7.2, work and energy in throwing a baseball. Here, there's a baseball and you throw a baseball in upward direction. So in example 7.1, where is it? This example we have already discussed. Suppose your hand moves upward by 0.5 meter while you are throwing the ball. The ball leaves your hand with an upward velocity of 20 meters per second. Find the magnitude of the force assumed constant that your hand exerts on the ball. Find the speed of the ball at a point 15 meters above the point where it leaves your hand. Ignore a resistance. Here we define three positions. Y1, where the baseball and hand are at rest. And here, this is the Y2. I put this Y2 is origin. I can do that, okay? Then, at this condition, the velocity of the baseball is 20 meters per second. And here, this is the position 3, where the height is 15 meters above the point where it leaves your hand. And here we have velocity 3. So since I have chosen this position is origin and this position is positive 15 meter, this position must be minus 0.5 meter. So your hand moves upward by 0.5 meter while you are throwing the ball. So I move my hand 0.5 meter upward direction, okay? Since this is the origin, this is the initial position of the hand, it must be minus 0.5. So now let's discuss the energy of the ball. Here on the right side, I have again colored energy columns. So this is the total mechanical energy. This is the kinetic energy of the baseball. This is the gravitational potential energy of the baseball. What about the kinetic energy of the baseball here? It is 0 because velocity is 0. What about the gravitational potential energy of the baseball here? It is not 0 because I have chosen this is the 0. This is the origin. Here I have minus. Then I have negative gravitational potential here. Don't forget. And at this condition, the baseball, in the second condition, baseball has certain velocity. For this reason, it has kinetic energy. Since it is at the origin, gravitational potential energy is 0 because gravitational potential energy is given with this expression. Gy. Since y is 0, then this will be 0, okay? Here we have 0 gravitational potential energy. And the total mechanical energy is only given with the kinetic energy of the baseball. So now look at the total mechanical energy of the baseball at this condition. We have some certain velocity. For this reason, we have some kinetic energy. Now we have certain height. We have gravitational potential energy. And now total mechanical energy is given with K3 plus U3. Here, the total mechanical energy E2 is given with K2 plus U2. And here, the total mechanical energy for the first condition is given K1 plus U1. Find the magnitude of force that your hand exerts on the ball. Find the speed of the ball at a point 15 meters above the point where it leaves your hand. Ignore air resistance. When the ball is here at the position 3, let's say, what about the forces acting on this baseball? Only weight is acting, okay? Downward direction. But what about here in this condition? And what about here in this condition? Here in this condition, we have weight, and until it reaches to this condition, we have F other. What is this F other? I apply a force with my hand to move this baseball in upward direction, okay? So you must be very careful. Here at this condition, F other is 0, but here at the beginning, between Y1 and Y2, I have F other, okay? And what about the work done by F other? Here in this case, the work done by F other times S. What about the displacement? The baseball is moving upward direction and I apply F other upward direction, then it will be positive here, okay? What about the work done by gravity here? The work done by gravity here is negative because displacement upward direction. Now let me clean this part and continue to the solution. I think now the question is clear. Okay, this is the solution. So let's calculate V other. What was V other? V other done by hand on the baseball, work done by hand on baseball. And at the beginning, here in this condition, kinetic energy is 0 because it is at rest. And gravitational potential energy is given with minus this value because height is negative, okay? This was the origin, and here we have negative. And then here we have negative gravitational potential energy. And what about the kinetic energy at the position 2? Since we know the velocity at the position 2, we can calculate the kinetic energy with this one. Okay, and what about the gravitational potential energy at the position 2? It is 0 because it is staying at 0. I have chosen this is the origin. So initial kinetic energy, initial gravitational potential energy, final kinetic energy, final gravitational potential energy. Okay, so then put them here together. K1 plus U1 plus other work is equal to K2 plus U2. And if I take other work done on the baseball, then I can get this expression. So if you put all these things into this equation, then you can calculate other work. So what is V other here? V other is given with F applied by your hand and displacement. Okay, displacement is 0.5 meter, which is given 0.5 meter during this movement from this position to this position. We apply this force F other. Okay, and then we know the V other, we have already calculated, put it there. Finally, we can calculate the force that your hand exerts on the ball. What about the second question? Find the speed of the ball at a point 15 meters above the point. Okay, so where is it? You can write this expression. So this is the position 2, this is the position 3. And between position 2 and position 3, only gravity acts on the particle, since we have considered that air resistance is ignored, okay? And I don't apply any force on the ball in this case. So then I can write this one. So the other here is 0, okay? There is no other force. So then final mechanical energy at the position 3 is equal to the initial mechanical energy at the position 2. So if you write all these things into the equation, then finally you can calculate this expression, 10 meters per second. Any question here? Now let me continue with work and energy along a curved path. So up to now we have discussed the work and energy along a straight line. So now we have a box, and this box here in figure A is moving in this way, okay? It is a curved path. So let's consider that here there's a F other. You can consider tension force or something else, or normal force, okay? Here we have F other, and here we have weight. So then what about the work done on this box? In order to find the work done on this box, we can find the work, gravitational work, by using the small segments of displacement. Here, let's consider that this is the same path, okay? Same curved path in B. And here we have delta S, very small segment of displacement along the curved path. So this delta S has X component delta X and Y component delta Y. And this is the weight acting on the object due to gravity, which is given with mg. And what about the sign of the delta Y? Delta Y is negative. If you choose, this is the negative Y direction, okay? So now let's try to calculate work done by gravitational force. I can write the gravitational force with this expression, m times g. G is the acceleration and it is vector. And I can write this g vector with minus g times j, because g is along the negative y direction. And what about the displacement? Delta s vector displacement can be written with delta x times I, x component of the vector, plus delta y times j, y component of the vector. And the gravitational work done on the box is given with weight times delta S. This is the scalar product, okay? Then it is given with minus mg j times delta S. Since this is the scalar product or dot product, this j and I will give us 0, then this J times J will give us this result, minus mg delta y. So what about the sign of the gravitational work on this box? This is the direction of the displacement delta y, and this is the direction of the weight. Since they are in the same direction, this gravitational work done on the box must be positive. Here you see a negative sign, but here what about delta y? Delta y is also negative, okay? Displacement is negative along the negative y direction, then negative times negative, this will give us positive number. So we have positive gravitational work. And what about the work done by other forces? Let me draw here. I'm talking about special condition. If other force, F other, is perpendicular to the displacement, this was the displacement delta S, then the work done by other force will be 0, because the other is equal to F other times delta S, F other. So what about the cosine 90? I can also write this one, F delta S cosine 90. Cosine 90 is 0, then the other will be 0 if F other is perpendicular to the displacement in a curved path. Do you have any question here? Then here I have minus mg delta y. Okay, so what is delta y? Delta y is total vertical displacement, final position minus initial position. So instead of delta y, use here y2 minus y1. And I can also write this one, mgy1 minus mgy2. So what is this? This is the initial gravitational potential energy, and this is the final gravitational potential energy. And here we have gravitational work on this box on a curved path can be written minus delta U gravitational, right? So what do you see? This is the same expression for gravitational potential energy along a straight path, okay? So we can use the same expression for gravitational potential energy, whether the body's path is curved or straight. So now let me continue with the conceptual example here. Energy in projectile motion. A batter hits two identical baseballs with the same initial speed and from the same initial height, but at different initial angles. Prove that both balls have the same speed at height h if air resistance can be ignored. So total mechanical energy is conserved, okay? Kinetic energy plus potential energy at the first condition is equal to kinetic energy plus potential energy at the final condition. This is valid for both balls, okay? Here, let's consider that this is the initial condition and I choose it is origin, and they start with same velocity, same speed, okay? So if they have same speed, it means that ball A and ball B have same kinetic energies at the beginning. So now let's write kinetic energy of the ball A, which is equal to 1/2 VA square, and it is equal to the VB square, because it is given two identical baseballs. It means that they have same mass, same initial speed. It means that VA is equal to VB, okay? So same initial height, it means that initial potential energy of the baseball A is equal to initial potential energy of the baseball B. So at some certain height, this baseball A is here and baseball B is here. And what about their kinetic and potential energies? Since the total mechanical energy is conserved, and since they have same kinetic and potential energies at the beginning, so here at certain height, since they are identical, they have same potential energy and they will have same kinetic energy. Then they will have same speed at the same height if the air resistance can be ignored. And what about the energy columns here? This is the total mechanical energy for both case. So at the beginning they have kinetic energy and gravitational potential energy is 0 because I have chosen that this is the origin. And at this height, we have same total mechanical energy as this initial case, but some part of this total mechanical energy goes to the gravitational potential energy due to the height, and some parts of this total mechanical energy goes to the kinetic energy. And at the maximum height, for example, for this one, for this ball A, at the maximum height, kinetic energy is 0. Okay, and gravitational potential energy is maximum. For this ball, it happens here. Okay, any question here? I hope it is clear. Then let me continue. Example from the book, speed at the bottom of a vertical circle. Here we have a vertical circle. Your cousin Throckmorton skateboards from rest down a curved, frictionless ramp. There is no friction on the surface of this ramp. If we treat Trocky and his skateboard as a particle, he moves through a quarter circle with radius r 3 meter. This is the radius of the circle which is given. Find his speed at the bottom of the ramp. Find the normal force that acts on him at the bottom of the surface. So what is the normal force here? Normal force at this condition. So here we have a free body diagram on the right side. This is the initial position. This guy, this child here is at rest, and there is a weight acting on this one, and normal force is 0 because what do you see here? This is the weight, and this guy here does not apply any force on this surface at this condition. For this reason, normal force is 0. And whenever the curve changes, we have normal force perpendicular to the surface, and there's a weight, and normal force, weight, normal force, weight, normal force, weight. So what do you see here? The magnitude of the normal force increases with the position. Okay, you will see at the end of the solution. Okay, now let me continue. So I need the velocity here and I need normal force here. The only forces on Truckee are his weight and the normal force exerted by the ramp, although N acts all along the path here. Okay, it does 0 work because N is perpendicular to Truckee's displacement at every point. This is very important. Here we have F other. This is normal force, F other, but it does 0 work on the guy because, let me show you, what about displacement? Here displacement is like this. Here displacement is like this. Here displacement is like this. Here displacement is like this, and here displacement is like this. So what do you see here? That this normal force is always perpendicular to the displacement. For this reason, there is no work due to the normal force, okay? F other is 0. And we have also considered that this surface is frictionless. Then V other will be 0, and the total mechanical energy will be conserved, okay? So we treat the trachea as a particle located at the center of his body. Take point 1 at the particle's starting point. This is the particle's starting point. And take point 2, then I choose this point, y is equal to 0. This is the point 2, okay? This is the ground. This has some certain height. This height is given with r, radius of this circle. And we take the positive y direction upward, then the y1 r and y2 is 0, okay? So trachea starts at rest at top. So velocity of the trachea here at this condition, v1 is 0, okay? And we are looking for his speed, v2 here. What is v2? This is asked. So in order to find the normal force, where is it? It is asked, find the normal force in part B. We will use Newton's second law, and we will have this relation. Since the trachea has this type of movement, it is circular motion, and there is an acceleration inward direction, which is given with v square over r, and then I can calculate the n. So now let me clean this part and complete the solution. Kinetic energy at the point 1. It is at rest, it is 0. Gravitational potential energy at point 1. Here, the height is given with r, okay, because the radius of this circle is r, then this is also r, then I have height, this is the y1 is equal to r, then gravitational potential energy is mgr. So what about the kinetic energy at position 2 here at point 2? Kinetic energy is given 1/2 mv2 square, and the gravitational potential energy here is 0 because I have chosen that this is 0, okay, origin. Then since the mechanical energy is conserved because there is no other work done on this guy, then mechanical energy is conserved. E1 is equal to E2. Then E1 is given with this one, E2 is given with this one. So put the kinetic and gravitational potential energies into this equation, and then finally you can calculate V2 as 7.67 meter per second. So what about the A radial? Since we have this type of movement here at just this position, A radial is given with V2 square over R. And what about the V2? V2 is this one I have calculated here. Just take this V2, put it there, take the square of this one, 2gr over r, this r will cancel this one, and then A radial will be 2g, okay? A radial is 2g here. Then what about the net force acting on the guy here at position 2? Net force along the y is normal force, upward direction, minus weight, and it is equal to m times A radial. And then instead of A radial, just use 2g, okay? And then I have here 2mg, and take normal force from this expression, then weight plus 2mg, and weight is mg, 2 mg here. Finally, n is equal to 3 mg, okay? So you know the m, you know the g, then you can calculate the normal force. Any question here? Okay, let me continue. So if vertical circle with friction, the same question, okay? Here we have considered that there is no friction on the surface, but now we have considering that there is a friction on the surface. Due to the friction, the trachea has less velocity, less speed, okay, here at point 2 compared to the speed of trachea here in this condition, okay? So in this case, there is no friction, but in the second case, we have friction. So due to the friction, we will have less velocity. You can imagine this one. And it is given here, trachea speed at the bottom is only 6 meters per second. And what it was 7.67 in the first case, if the friction is 0. Okay, what work was done on the child by the friction force? Okay, so then you can write this expression again: initial kinetic energy, initial gravitational potential energy, final kinetic energy, then velocity is changed, then final kinetic energy will be changed, and final gravitational potential energy, if you choose that this is y2 is 0, if it is origin, then the gravitational potential energy is 0. So what about the friction force? Friction force is V other. You can write like this: E1 plus V other is equal to E2. E1 is K1 plus U1 plus V other equal to K1 plus K2 plus U2. And if you take V other from this expression, this is the work done by friction force, okay? You can get this expression. If you put all these values which you have calculated here and put them here, then you can calculate work done by friction force. It is negative, okay? The work done by the friction force is negative, then you have calculated it. And let's compare the total mechanical energy. This is the total mechanical energy at this point. It is only given with the gravitational potential energy, and there is no kinetic energy because at this point the guy is at rest. It has only gravitational potential energy. And finally here at this point too, there is a total mechanical energy which is only given with the kinetic energy because we have chosen that this is equal to y2 is 0. Then there is no gravitational potential energy here. But what do you see here? The total mechanical energy, E2, let's say, is smaller than the initial total mechanical energy because some part of the energy is lost due to the friction, okay, due to the V other, because V other is negative. Then let me continue. Example 7.6, an inclined plane with friction. Here there is an inclined plane and it is rough surface. It has certain friction on this surface and this is the angle 30 degrees, okay? We want to slide a 12 kilogram crate up a 2.5 meter long ramp inclined at 30 degrees. This is the length of the ramp, which is given, okay? And this is the crate. A worker, ignoring friction, calculates that he can do this by giving it an initial speed of 5 meters per second at the bottom and letting it to go. But the friction is not negligible, so there is a friction on the surface. So due to this friction, the crate slides only 1.6 meter up. So normally the length of this ramp is 2.5 meter, but this box only slides up to this point, which is given with 1.6 meter, okay, and stops there, then slides back down. So it stops here and then it goes back, okay. To find the magnitude of the friction force acting on the crate, assuming that it is constant, how fast is the crate moving when it reaches the bottom of the ramp? So again, you will use the relation between kinetic energy and potential energy, and here you have to consider V other due to the friction force, okay? Don't forget. And what to do? So let's put some numbers and give name on the positions. Here we have point 1, position 1 at the beginning, and this is the position 2 at the maximum height, let's say, and then it goes back. This is the final position, it goes back, okay? So now let's try to write the kinetic energy, potential energy, and also V other at that points. So let's do that. At the beginning, kinetic energy is given with this expression. This was the velocity provided by the worker, okay? This is 150 joule, and the gravitational potential energy is 0 at the beginning because I have chosen that this is y is 0. This is the origin, okay? I can choose any point as origin. Then what about the kinetic energy at this position 2? At the position 2, the kinetic energy is 0 because velocity is 0 because it stops here. And then gravitational potential energy is maximum. You can calculate this one. What about the height? Height is given with 0.8 meter. You can calculate it. This is given in the question, 1.6 meter, and the angle is given. Then you can calculate this height. So height is 0.8 meter. Then gravitational potential energy is this one. So here we have V other. This is negative F times S. What is F? I don't know the F, but what about S? S is known. S is this one, displacement along this path, 1.6 meter, okay? So then just write the equation. K1 plus U gravitational 1 plus V other is equal to K2 plus U gravitational 2. Then if you take V other from this expression, which is equal to minus Fs, it is negative, don't forget. And then put all these things into this equation, then you can find this friction force 35 Newton, okay? Friction force is 35 Newton. And what about the second question? How fast is the crate moving when it reaches to the bottom ramp? You can do the same, okay? This is the position 2, and this is the last position, position 3. So again, you can write all these equations, okay? You can find the velocity of the crate when it reaches the bottom of the ramp. I will not go into detail due to the limited time, so you can do it by yourself. It is very easy to understand. So now let me continue with elastic potential energy. During the last lecture, we have discussed the spring, and we have discussed the stretching and compressing the springs, and we have discussed the force applied by hand on this spring and force applied by the spring on this hand. Okay, you have learned all these things, and we have also learned that the work done on a spring, which is given with the 1/2 kx2 square final position x2 minus 1/2 kx1 square initial position. Okay, so we have learned that this is the equilibrium condition. Here, the spring is at rest in equilibrium. Okay, and if you stretch it like this, you have to apply this force, and this force is not constant. It changes with position, okay? And when you apply a force in this direction to the right and to the left, spring applies an equal force on you, okay? So then the work done on a spring is written with this expression. We have done it during the last lecture, and the same work with the negative sign done by spring on your hand, and this work is called as elastic work done by the spring, okay, which is given with 1/2 kx1 square minus 1/2 kx2 square. So why the sign of this work done by a spring is negative compared to the work done on a spring? Because look at this equation which we have done during the last lecture. Here there's a fx, and if I choose this side is positive x, this force applied by hand and applied on spring, and this spring applies the same force with negative sign, okay, along the negative y direction. So if you write this force here instead of fx, minus kx, and here you will have minus kx, and you have to multiply this one with minus, okay? Then the result will be 1/2 kx1 square minus 1/2 kx2 square. So what do you see here? That work done by spring, okay? This one. This is elastic work, okay? Done by spring on hand. So now let's discuss different conditions, how a spring does work on a block. Here we have a block. Please carefully listen this part. If you understand this transparency, other transparencies will be very easy for you, okay? Very simple, just concentrate. So here the spring is neither stretched nor compressed. It is in equilibrium. It is at rest. It is staying at zero position, okay? Then I am applying a force, okay? Then I am stretching the spring. Then what about the force applied by spring on this box? Spring applies this force on this box, but what about displacement? I am pulling this box, and displacement is in this direction to the right. And what about the force applied by the spring? So work done by spring here is negative, okay? Because the direction of the force applied by the spring on this box is opposite to the direction of the displacement S. So then the work, spring or elastic work, is negative here, okay, in this B condition. Here, what about elastic work? It is zero because there is no displacement. What about C, third condition? So at the beginning, the box is here, and you are holding this box to keep it there, okay? And then you release it. Whenever you release this box, there is F spring, okay, in the negative X direction, let's say, and the box is moving along the negative X direction. Since both displacement and F spring are in the same direction, here elastic work is positive, okay? And look at this one, you compress the spring and the box is here, okay? The box is here and you compress the spring and you release the box. Whenever you release the box, F spring is in positive X direction and the box is moving along the positive X direction. then elastic work is again positive. Okay, so you must be very careful with the sign of the work done by spring on the box. So depending on the stretched or compressed condition, and depending on the direction of the force, direction of the displacement, the work done by the spring changes. It can be negative, it can be positive, or it can be zero, as we have shown here. Any question here? So here you see 1/2 kx1 square and 1/2 kx2 square. So what is this one? This is the potential energy, elastic potential energy. This is the elastic potential energy when the position is x2 and when the position is x1. So elastic potential energy stored in a spring is given with this expression. Let's consider this one. This is the ground and this is the spring. Let's consider this is the x is 0, equilibrium. And this is the distance x. So this was the equilibrium. When you apply force on this box and put it to the right side here, this Neve condition, okay, you store energy in this spring. And the magnitude of this energy is given with this one, 1/2 kx square, okay? Also, in the case of compressing, let's consider that again here, this is the initial condition. And you compress the spring like this. And let's consider this is x, okay? Again, you store this energy. So if the spring is staying at the equilibrium at the 0 position, there is no energy stored in the spring. But whenever you stretch or you compress the spring, you store energy into the spring, and this energy is called as elastic potential energy stored in a spring, okay? So what about the sign of the x? If it is stretched in this condition, then we have positive x. And if it is compressed in this condition, then we have negative x. But since you take the square of this x here in this equation, so this elastic potential energy is always positive, always positive, always positive, don't forget. So then work done by elastic force can be written in this form, 1/2 kx1 square minus 1/2 kx2 square. So this is the initial elastic potential energy, and this is the final elastic potential energy. And I can write this one minus delta U elastic. Why? Because it is written like this, okay? This is the delta U elastic. The change in the elastic potential energy. So remember the gravitational work, which is equal to the change in the gravitational potential energy. And here we have the work done by the spring, the work done by the elastic force is equal to minus the change in the elastic potential energy. Any question here? Then let me continue. So the work energy theorem says that the total work done on the object is given with the change in the kinetic energy. The total is equal to delta K, okay? We have done it in the past. So no matter what kind of forces are acting on a body, okay? If we have only elastic force does work on the body, then the total is given with the work done by elastic forces and it is equal to minus the change in the elastic potential energy with this term. So this V total is equal to delta K, and it is equal to K2 minus K1, and here it is equal to U elastic 1 minus U elastic 2, and if you take this 1 to this side, take this 2 to this side, so finally you can get this expression. Initial kinetic energy, initial elastic potential energy, final kinetic energy, final elastic potential energy. And total mechanical energy also conserved. So here we have total mechanical energy E1 first case and E2 in the second case or final case, okay? So if there are no other forces, total mechanical energy is conserved, and this total mechanical energy is written with the sum of kinetic and elastic potential energies, and it is conserved. So now let me discuss the elastic potential energy and kinetic energy. So this is the total mechanical energy at the beginning. This is the total mechanical energy at the final condition. Look at this one. Figure A. Here we have a mass and we are in equilibrium. Spring is not stretched, spring is not compressed. So what about the kinetic energy of the box? It is 0. What about the elastic potential energy? It is also 0 because it is not compressed. Remember that this elastic potential energy is written with kx1 square. Since x1 is 0, then it is 0. Look at this condition on the right side, B. Here we have, in the second case, U elastic potential energy, which is given with 1/2 kx2 square. Okay, so we have certain elastic potential energy stored in this spring. Okay, and kinetic energy is 0 here. Whenever you release this box, okay, this elastic potential energy will be converted to the kinetic energy, and this box will have certain velocity. Okay, so as here, when you release the box, due to the stored elastic potential energy here in this condition, this elastic potential energy will be converted to the kinetic energy, and there will be velocity of the box here. And again here in D, you compressed the spring. This is the initial position of the box, and you store elastic potential energy. Kinetic energy is 0 here when it is compressed. Whenever you release this box, this stored elastic potential energy will be converted to the kinetic energy, and this box will have certain velocity due to the kinetic energy. Okay, so this relation is very important in the questions or problems related to the elastic potential energy and kinetic energy. Any question here? Okay, here I would like to give you one more information. If you write this equation, it means that you are talking about ideal spring. In ideal spring, that we have been discussing must also be massless. Okay, if the spring has mass, it also has kinetic energy as the coils of the spring move back and forth. Okay, so if the spring has certain mass, then this spring will have also kinetic energy, and you also have to consider this one within this equation. But in many problems, we ignore the kinetic energy of the spring because we consider that the spring is massless. Okay, don't forget this one. Or sometimes the mass of the spring is very small compared to the mass here. Look at this one. Here we have a mass and here we have a spring. And if the mass of this box is much bigger than the mass of the spring, then again, you can also consider that this is zero, okay? And you can apply this rule. Very important example is the springs in the suspension system of the automobiles. So let's consider that here there is an automobile, there are wheels, and there are springs here. Okay, let's consider there are springs here. And since the mass of this car is about 1.5 ton, let's say, okay, and the mass of spring is very small compared to the mass of the automobile, then you can ignore the mass of the spring. Then you can still apply this energy conservation of mechanical energy. Okay, now let me show you the elastic potential on this graph. So the shape of the graph is a parabola. This is the x-axis. Let me draw here. This is the x. This is the x is 0. And the box is staying here. And this is the spring. So when the spring is stretched, now we are talking about this condition. This is the x, okay? X is positive, and we store energy here. This is the elastic potential energy, which is given with 1/2 k x squared. We store energy. Then when you release this one, this elastic potential energy goes down. So where this elastic potential energy goes? This elastic potential energy goes to kinetic energy. Okay, here you store the elastic potential energy, maximum elastic potential energy, but the kinetic energy is 0. But during the movement back to the equilibrium condition, you spend the stored elastic potential energy to increase your kinetic energy. And at this position, when the x is 0, you have the maximum kinetic energy. Okay, and when you compress the spring, and now the mass is here, okay, you compress the spring completely, let's say. Let me show it like this. Okay, you compress the spring. This was the initial condition, x is equal to 0. And then again, you store the maximum elastic potential energy, which is given with kx squared. Okay, and then this elastic potential energy is converted to the kinetic energy if you release this mass and if this box moves in this direction. So the behavior of the elastic potential energy is a parabola, as a function of the position. Okay, and I have already discussed that elastic potential energy is never negative, because if you put here negative number, or if you put here positive number, since you take the square of the x, this will have always positive number or 0. Okay, let me give you 2 examples. This is the leg of human, and here you see Achilles tendon, okay, and here there's a calf muscle, and here there's a heel bone, okay. the Achilles tendon acts like a natural spring, okay? I have also given some biological examples and applications in the previous lectures. So tendons can be stretched or compressed, okay? They can behave like a spring, okay? We have already discussed this one. And how to do that? Muscles apply forces on tendons and then they can be compressed or stretched. When it stretches and then relaxes, this tendon stores and then releases elastic potential energy. With this one. This is the magnitude of stretching and compression. This is related to the properties of the tendon, okay? Then you store elastic potential energy in the tendon. So this spring, this tendon action, this spring action reduces the amount of work your leg muscles must do as you run. So this tendons help us, okay, during walking. And here another example, bioapplication, elastic potential energy of a cheetah. When a cheetah gallops, its back flexes and extends dramatically. So look at this condition. So let's consider that this is x is equal to 0. Okay, and let's consider this cheetah is completely a spring, okay? And what do you see here? At this condition, it is stretched, okay? It is stretched and elastic potential energy is stored. Okay, so this elastic potential energy is spent to run this cheetah faster, okay? Flexion of the back stretches tendons and muscles along the top of the spine and also compresses the spine, storing elastic potential energy. When the cheetah launches into its next bound, this energy is released, enabling the cheetah to run more efficiently. So this stored elastic potential energy is converted to the kinetic energy, okay? Now let me continue with the situations with both gravitational and elastic forces. So within this lecture, up to now, I have investigated gravitational potential energy separately, and I have investigated elastic potential energy separately, okay? So what happens if we have both of them in the question, okay? Now you have to write total work done on the object is the work done by the gravitation, the work done by the elastic forces, and the work done by other forces. They can be tension force, friction force, push force, okay? So this is the total work done on the object with the forces. If you apply work energy theorem, what was the work energy theorem? Work energy theorem tells that the total work done on the object is given with the change in the kinetic energy, okay? So then it is equal to gravitational work, elastic work, and other work done by other forces. So instead of gravitational work, you can write this one. We have already done it. And instead of elastic work, the work done by elastic forces, you can use this one. So put them here. K1, U gravitational 1, U elastic 1 plus V other is equal to K2, U gravitational 2 plus U elastic 2. Okay, don't forget this formula. Keep always in your mind. Okay, what do you see? Initial kinetic energy, initial gravitational potential energy, initial elastic potential energy, and V other. This V other can be positive, can be negative, or it can be 0. And final kinetic energy, final gravitational potential energy, and final elastic potential energy. Okay, we have this one. What we have here, we have gravitational potential energy and elastic potential energy. Here, gravitational potential energy and elastic potential energy. Then I can combine them in a single potential energy, U1, and I can combine this one in a single potential energy, U2. Then here we have initial kinetic energy, initial potential energy, which includes elastic potential energy and gravitational potential energy plus the other. And here we have initial final kinetic energy plus final potential energy of all kinds, includes, let's say, gravitational potential energy plus elastic potential energy. So here, what I also would like to tell you, and here we have the other, as I have told you, this is the initial mechanical energy of the system. This is the final mechanical energy of the system. And here we have the other, okay? So if this V other is positive, then final mechanical energy will be bigger, and then mechanical energy is increased. If this V other is negative, then mechanical energy is decreased. If this V other is 0, then initial mechanical energy is equal to the final mechanical energy, then mechanical energy is conserved. Okay, don't forget these three conditions. And now let me discuss this example, and then I will continue with 3 examples from the book, and then I will finish. Here you see a trampoline and you see a child. So what kind of forces acts on this child and what kind of energies you have to consider within the energy equation? Trampoline jumping involves an interplay among kinetic energy, gravitational potential energy, and elastic potential energy. Due to air resistance and friction forces within the trampoline, mechanical energy is not conserved because there is air resistance and friction forces within the trampoline. That's why the bouncing eventually stops unless the jumper does work with his or her legs to compensate for the lost energy. So let me write the energies. Initial kinetic energy plus initial gravitational potential energy, initial elastic potential energy plus the other, okay, final kinetic energy, final gravitational potential energy plus final elastic potential energy. Okay, this is the equation. So what is the V other here? The other, you can consider friction forces here within the trampoline and also friction forces in the air friction, okay? The other is this one. So this is the initial mechanical energy, and here we have the other, and here we have final mechanical energy. Due to the V other, some parts of the energy is lost, then finally this child will stop. But if this child does work with his or her legs to compensate for the lost energy, okay? So to compensate the loss due to the V other, he can apply or she can apply forces by using muscles on his leg. So now let's discuss the situation here. What happens during this jumping? As the jumper descends through the air from the high point of bonds, gravitational potential energy decreases and kinetic energy increases. Okay? Here at this condition, let's consider this is the trampoline and this is the child. And here, let's say at the maximum height, kinetic energy is 0 and it has maximum gravitational potential energy at this certain height, okay? And when he is moving downward, some parts of the gravitational potential energy is converted to the kinetic energy. Now kinetic energy is different from zero, okay? And gravitational potential energy decreases when he is moving in this direction. Whenever he touches on the surface of the trampoline, let's consider this is the y is 0, gravitational potential energy is 0, and kinetic energy is maximum. And this kinetic energy is used to compress this trampoline, okay? This trampoline will be compressed like this in the last condition, okay? Then look at this one. You compress this trampoline with some certain distance, delta y, okay? And then you store elastic potential energy with this expression, K delta square, okay? And there's a gravitational potential energy here because now we have gravitational potential energy, which is given mg delta y here, okay? And kinetic energy is 0 here. Then this stored elastic potential energy will be converted to the kinetic energy, and this child will jump again in this direction. So this is the relation between gravitational and elastic potential energies and also kinetic energy. So you can investigate all these things within this example. And of course, you also have to consider sometimes air resistance and also friction forces in the trampoline. Then you have to consider other work done by other forces on the object. Any question here? Okay, let me continue. Example 7.7, motion with elastic potential energy. A glider with mass 0.2 kilogram sits on a frictionless horizontal air track connected to a spring with force constant 5 Newton per meter. Let's consider this is the air track. Okay, and here there's a spring, and here there's a mass, and this surface is frictionless, and there's a mass here. You pull on the glider, stretching the spring 0.1 meter and release it from rest. The glider moves back toward its equilibrium position, x is equal to 0. What is its x velocity when x is 0.08 meter? So this is the position 2, point 2. You stretch the box. It was relaxed at the beginning when the x is equal to 0. It is in equilibrium, but you stretched it, okay? And now what is the x? X is this one. So you store energy here, okay? And kinetic energy is 0 here because it is at rest. And when you release this mass, this stored elastic potential energy will be spent for the kinetic energy. Okay, it will be converted to the kinetic energy. So then at certain position, which is given in the question, this box will have certain velocity, and the velocity is asked. Okay, so then let me calculate this velocity here. Kinetic energy is 0 because the mass is at rest here, and we have the potential energy stored, which is given with this expression. If you write the K, which is given in the question, and if you write the magnitude of the stretching, then you can calculate the potential energy. And here, what about the K2? In point 2, we don't know the velocity. We have to calculate this one. And we know the potential energy. Okay, you can calculate this one because this x is given. And if you apply this rule if there is no V other, if V other is 0. So within the question, the surface is considered as frictionless, okay, then V other is 0, then I can apply this conservation of mechanical energy and then put all these numbers here, then you can calculate the velocity, 0.3 meter per second. Any question? And let me continue with another question. Suppose the glider in this example here is initially at rest, okay, with the spring unstretched, x is 0 in equilibrium, spring is unstretched. You then push on the glider with a constant force in the positive x direction. So you apply this force in positive x direction, let's say. What is the glider's velocity when it has moved to x? This was x0. Now we have new x position, 0.1 meter. So how to find this one? Displacement. What about displacement? Displacement delta x is this one, 0.1 meter. And the initial kinetic energy here is 0. The initial potential energy here is also 0 because the spring is unstretched or uncompressed. And in this case, we have kinetic energy with this one, and we have potential energy this one, okay? This x is given, we have certain potential energy. But what about other forces? Is there any other force here? Yes, we have force. We have applied this force. Okay, at the beginning, there is no force here. But now in the second condition, I have applied a force along the positive x direction. So what about the displacement? Displacement is along the positive x, and the applied force is also along the positive x, and V other will be positive due to this applied force. And I know the force which is given in the question, magnitude is given, and I know the displacement delta x, then I can calculate the V other. So just put all these things into the equation. So how to do that? K1 plus U1 plus V other is equal to K2 plus U2. Okay, since this V other is positive, then this initial mechanical energy here, final mechanical energy here, the mechanical energy is increased. Okay, so we will have bigger mechanical energy compared to the initial case due to the positive V other here due to the applied force. Any question here? Then this is my last example, and then I will finish my lecture. Example 7.9, motion with gravitational, elastic, and friction forces. A 2,000 kilogram elevator with broken cables in a test rig is falling at 4 meters per second when it contacts a cushioning spring at the bottom of the shaft. Here is the picture. This is the cushioning spring. You see, this is the elevator, and this is the cable. Cable is broken. The spring is intended to stop the elevator, compressing 2 meters as it does so. During the motion, a safety clamp applies a constant 17,000 Newton friction force to the elevator. What is the necessary force constant K for the spring? Let me explain the question. Here, there is an elevator, and this is the cable. This cable is broken, and here we have safety clamps here, safety clamps in order to provide friction force to stop this elevator, okay? These are the safety clamps, and you can also see these safety clamps here, okay? Actually, there must be a cable, but it is broken. And there is a spring here, cushioning spring, okay? So when this elevator touches this spring, it has velocity of v1, 4 meters per second, and the friction force due to this clamps is given 17,000 Newton, and the mass of the elevator is also given. So the question is, what is the force constant of this cushioning spring? Okay, so what to do? Here we have point when the elevator touches to the spring, when the spring is relaxed. Let's consider that this is the y is 0 position for the spring, and then spring is compressed with 2 meters, and this is the position 2, okay? Elevator applies a certain force, and then spring is compressed, okay? Now let's write the equation. The elevator's initial speed is v1, so the initial kinetic energy is this one, k1. The elevator stops at point 2, so at point 2 here the kinetic energy is 0, and at point 1 the potential energy is 0. What about the potential energy? Potential energy is given with this one, total potential energy. Gravitational potential energy plus elastic potential energy. Why gravitational potential energy is 0? Because I have taken that this level is y is 0, okay? So then your gravitational will be 0 here. What about elastic potential energy? Since the spring is staying at the equilibrium, there is no compression, then your elastic is also 0, okay? At the first case. Let me clean this part and then continue. So at point 2, there are both gravitational and elastic potential energies. So the total potential energy is given with gravitational potential energy at point 2 plus elastic potential energy at point 2. This is the total potential energy at point 2. Why? Because we have compressed the spring with 2 meters, and this was the y is 0. Now we have y is minus 2. Then we have u gravitational also here, which is different from 0. Then let's continue. What about the work done by the friction force during this movement? So there is a friction force in upward direction due to the safety clamps here, okay? So the displacement is in downward direction, but the friction force is upward direction. Then V other due to the friction is given with minus F times displacement minus 34,000 joule, and just write the equation. Initial kinetic energy, initial total potential energy, V other final kinetic energy, final potential energy. And here, initial kinetic energy is given. We have calculated this one. You can put it there. Initial potential energy is 0 because there is no elastic potential energy. There is no gravitational potential energy at point 1. I have already discussed. And here we have V other. And here we have final kinetic energy. The elevator is stopped. Then the final kinetic energy is 0. Put it 0 there. Then this is the final gravitational energy, final elastic potential energy. Then we know the V other. We have already calculated. Put it there. So what we have here, mg y2, gravitational potential energy, 1/2 k y2 square. I know y2. I know y2, I know mg, and k is unknown, okay? And in the question, what is the necessary force constant for the spring? So if I take this K from this equation, then I can calculate K force constant, 1.06 times 10 to 4 Newton per meter, and this is about 1/10 of the force constant of a spring in automobile suspension. We have given this information in automobile suspension systems. It is in the order of 10 to 5 Newton per meter. So with this one, I finish my lecture. Next lecture, I will continue with the conservative and non-conservative forces. Do you have any question? Then take care of yourself. Bye-bye.